Okay, let's continue with the proof systems that we stopped. I think we stopped here last time. Let me just, since it's been a week. By the way, there's makeup tomorrow. So we have next 3 weeks, probably we'll have 2 lectures on Tuesday and 2 lectures on Wednesday. So it's at 3 tomorrow, I think. So the lecture tomorrow starts at 3 instead of usual 4. Okay, anyways, so let's recall very quickly what were the proof system. Proof system was 4 things. We talked quite extensively. So you have things, the symbols you can use, your alphabet, your language, so things you want to be able to write down, the expressions, so to speak. This language should be decidable. Of course, you should be able to recognize if the string is in your language or not. Then you have a set of axioms, which is also decidable. You should be somehow algorithmically be able to tell whether some string is an axiom or not. And then you had the decidable proof rules, meaning that if you have some I many strings, what does it mean that this I many strings derive one string V? And the example of this proof rule would be modus ponens, which is if you have A and A implies B, you have B. But you think of it as just purely syntactically, this means nothing. This is just a string. If you have this string and this string, then you have this B, this string B. And then the proof was just sequence of strings such that each one of them is an axiom or it's derived from the previous ones. Right? And this is very important notation that you have a proof system S. If there exists a proof, meaning the string like this, such that each one of them is an axiom or can be derived from the previous one, this means that we write it as S, this symbol here, WT. Well, WT is the last string that you derived with a proof. And I want to remind you about this because we'll get back to this, that first of all, set of proofs in your system is decidable, meaning that if I give you a proof, there's an algorithmic way. By algorithmic, I mean there exists a Turing machine, which is, you can think of it as it is a definition. We take it as a definition of an algorithm. So there exists an algorithm that given a string, it tells me if this string is a proof or not. And what it does, just has to check syntactically this thing here. So it has the string, so it checks is W0 an axiom, then it checks is W1 an axiom. If not, is it derivable from W0 with R? Since R is decidable, it can check all the R's and everything. We talked about this last time. So set of proofs is decidable, meaning algorithm can check whether something is a proof or not. You might have heard about the proof checkers. That are quite famous recently, that many famous people work on, but that's besides the point. So they actually do this, create algorithms that actually check proofs and stuff. And then the next one, which we will get back to hopefully today or tomorrow, is that we said something like the set of provable strings is recursively enumerable, meaning this is very different from this one. Why? This one, decidability of this one means I give you a proof, I'll give you a string, and you tell me it's a proof or not. But now, can I do the same thing with a string? Not the same thing, but what if I give you a string and you're supposed to tell me does there exist a proof for this or not? So decidability of this thing is quite different from this thing. This guy just recognizes proofs. However, this guy recognizes everything that can be proven, if such thing exists. And we don't know if such thing exists. We said it would be a paradise if such thing existed, meaning I give you a string, let's say the string that represents Goldbach's conjecture or Riemann hypothesis or something. I write it down as a string and I ask my algorithm, is this provable? And I always get an answer yes and no. That would be a paradise. That would just solve all mathematical problems. In some sense, it might be but it's clear. So okay, let's leave it aside. But it's what we prove here that it's a recursively enumerable, meaning there exists an acceptor for this. So if something is provable, I can eventually find a proof by just enumerating all possible strings. So I enumerate all possible strings, and for each enumerated strings, I test if it's a proof or not. If yes, I output whatever this thing proves. So this way, if I go on forever, I can enumerate all provable strings. But however, if my sentence, let's say Goldbach's conjecture or whatever, is not provable, I will never know somehow that it's not provable, because this just keeps enumerating provable things, and I never know, should I wait for Goldbach to come out or not? So it's very different than just this being decidable, which tells me no or yes on every answer. But set of provable strings is recursively enumerable. We discussed this last time. And then we started to build a most important example for us, which is elementary number theory. So I want to talk about elementary number theory. And what was my syntax? My syntax was I was using these symbols here. These symbols mean nothing for a computer or for an algorithm, but for us, we think of them as having some meaning. That's why we employ them in the beginning. But here, as they stand, they're purely syntactic. So 0, 1, VC, parentheses, plus, dot, equals, this is supposed to have and, or, not, implies, exists, any. So this is my alphabet. Of course, I can create many different strings from these symbols, which I do not care about. So the idea is to create strings. So my language should contain strings which express something. That's the idea. And then we talked about variables and constant symbols. So these things are like V and W is just, think of it, W as encoding a natural number in binary. So since I only need zeros and ones, so I can have V10, that I think of it as V2, like a variable V2. And C would stand for constants. Constants are different than variables. We'll see in a moment. We actually talked about this last time, but we'll see more things in a moment. And then we talked about free and bound quantifiers. So free and bound occurrences of variables. And let's not talk about it once again, because it's also in the recording. And so we'll discuss examples now, and we'll see. So maybe that would revive your memory also. Yeah, and very importantly, we discussed set of terms. What is a term? Term is constants are terms, variables are terms, and also if you have terms A and B, A plus B is a term and A times B is a term. So think of it intuitively. These are expressions in natural numbers. Somehow not natural numbers. So expressions so they are basically strings. They're nothing but expressions like this, like V10, think of it, V2 plus 1 is times C3. So it's something like this. So it's like an expression that contains variables and constants and ones and zeros. So it's basically correctly written expression is a term in a sense. And the predicate is an expression, so it's a term such that you can, in your head, you can assign truth value to. For example, this has no truth value, right? V10 plus 1 times C11 is not true or false. However, you can think of it predicate. What is a predicate? If you have terms A and B, A equals B is a predicate. Something equals something is already true or false, of course, dependent whether there are variables in here. We also discussed this, but then let me get back to this. So the arithmetic predicate was A equals B was a predicate, and then if you have predicates A and B, I have not A and B, A or B, or A implies B was also a predicate, right? And also I added these two quantifiers. If A is a predicate, then there exists Y such A, and for any Y, A is also a predicate, and that's it. For example, for any V0 and any V1, V0 plus V1 equals V1 plus V0 plus V10 would be a predicate. Of course, this still does not have a truth value, because this expression, if you think about it, this depends on the value of V10. It's sometimes, if you think of it as an expression of natural numbers, this is nothing but a string, but if you think of it as this being variables, all of them, then this depends on the value of this variable. If I plug in 0 here, this will be true. But if I plug in something else here, this will not be true. So the reason is because this predicate here has a free variable. v10 is a free variable, whereas v0 and v1 are bound by the quantifiers any here. Quantifiers any. So this was the distinction that we talked about, free and bound variables. You can define free and bound variables purely in a just syntactic manner. However, we think of them as this way. And we also mentioned that you do not have to use parentheses all the time. You just do priorities. You do multiplication first, then you do plus, then equality, and then you do not have to write parentheses at all, and you can completely remove them from here, but it's just cumbersome to write 1, 2, 3, 4 parentheses here. Okay, let me push this even farther, and then we stop and have a small discussion. So again, free and bound variables, I already mentioned, for example, this here. For any x, there exists y such that x plus 1 is y, and there exists y such that x plus y is 0, such thing. Okay, yeah, we'll discuss this. And yeah, this is where we stopped. And I'm going to say this, and I'm going to pause it for discussion and recall other things in Georgian. So what is a statement? A statement is a predicate without free variables. So this here is not a statement, because the statement is something that we think of in our heads either is true or not. This thing cannot be true or false because it depends on what v10 is, because v10 is a free variable. If it has no free variables, if you erase v10 here, or you write exists v10, so if I would have here, maybe I can write it down. If I would have something like this, exists v10, there exists v10 such that for any v0 and any v1, v0 plus v1 equals v1 plus v0 plus v10, this would be true. Because if there exists v10, namely 0, if you plug in 0 for v10, this would be true. But if I write, instead of exists, if I write something like this for any v, then this would be false. But if I do not write anything, and then this is a free variable, meaning it's free, then this has no truth value in our heads associated to it. This is what I'm aiming at. And the statement is a predicate without free variables. For example, this is actually a good distinction when you can see what is a difference between constants and variables. V plus V1 is not a statement because it has no truth value. But C plus C prime equals C prime plus C is a statement because I do not think of C's as variables, rather I think of them as constants. So it's like a fixed thing plus another fixed thing equals this plus this. This is a statement. However, if this were V's, then that would not be a statement, because then V's are variables. So here you can see what's the distinction between constants and variables. Also, in my language of elementary number theory, is collection of all statements. So it's basically strings which can have a truth value. For example, my Goldbach's conjecture, I don't know if we still have it here. I think here I wrote it. So Goldbach's conjecture is that every even number is a sum of two primes. And you can write it as a string. I don't know if this is correct or not. But for any s and for any n, if for any s and any n, which is 2 times k, so n is even, there exists p1 and p2 such that n is a sum of p1 and p2. And if s divides p1, then s is 1 or s is p2. So it's basically a string that says that every even number is a sum of 2 primes. And this would be a statement, meaning it will not have any free variables. All of them will be bound by quantifiers. So this either in our heads either has an answer yes or no. So either it is true for all natural numbers or not. Either every natural number is a sum of 2 primes, or there exists a counterexample. So the statement will be, so statements are basically exactly the strings that are supposed to capture statements about natural numbers. So let me pause this. So we'll quickly recall what the statements are in number theory. By the way, you can do the same thing for different theories. This, what we're building, so I have to still tell you what are the axioms of number theory and rules of inference, or what did we call them? Rules of inference or proof rules. So I still have to tell you to give you the complete. So I only told you the alphabet and the language, but I have to tell you axioms and other stuffs. But you can, okay, I'll get back to this when I finish it. But first, before we go on and tell you what are the axioms, I will tell you what is the truth. And what is the truth, even though I will try to tell you here, I'm basically shoving it under the rug. If you're really interesting, if you really hard think about it, so I'm gonna, okay, let's define it and then. So far, what I did is I just syntactically defined what strings are in my language. That's it. I have no notion if this string is true or this string is false. This was only in my head because I knew that this meant something for me. For example, n equals 2k means that's natural number which is even. But as for a string, this means nothing at the moment. Because this is just a simple string. It has no truth value. It's neither true nor false. For example, any. It's only in my head. So what I want to do is now I want to formalize such thing. And what I'm going to do is I'm going to push it into natural numbers. And I'm not going to talk about what it means for natural numbers to hold the truth. Okay, let me define it and then we talk about it. First of all, the first observation is the truth is only model specific. Or maybe I can give you an example that you know. You learned groups in algebra, right? So groups had some axioms, right? So 3, 4, I don't know how many. Yeah. So for example, you had this axiom here: x times z is the associativity, they would probably call it. So something like this. Then you had a string that there exists e maybe such that x times e is e times x and is x. Some neutral element or something. But think about it, these are just strings. These mean nothing. So this is actually building a proof system. And maybe then you had for any x there exists y such that xy is yx and it's e. So this is the inverse axiom. And then you had a special kind of, so let's call these guys were called, I don't know, commutative groups or abelian groups. So abelian groups where you had the special axiom number 4 is that x times y is y times x, right? Now I'm asking you, is this true? So it has no meaning to ask you whether x times y is y times x. It depends on what you're talking about. So what is a model? So now I can talk about the real world thing. So let's talk about natural numbers. No, let's skip natural numbers. Let's talk about integers. Is the first axiom true in integers? Yes. What about the second one? Yeah. So all 4 of them will be true in integers. However, let's talk about, I don't know, matrices, 2 by 2 matrices on real numbers. Are these axioms true? Which one? Yeah, number 4 is not true for matrices, right? So they would say that these 3 things, which constitute group, so groups are sets which are models for these 3 axioms, basically. Yeah, that's right. No, associativity is true. So this one is also true, but not every matrix has an inverse, yeah? So 3 and 4 would not be true. So something like, So the idea is that, that's very good. 3 and 4 will not be true for this guy here, but this would be true for, so all 4 of them will be true for z. Let me write it this way. But the idea that I'm claiming that the value of this string, whether this string is true or not, is meaningless. It only depends on the model that you're discussing in. So the truth value for this string somehow comes from the thing you're discussing these things into somehow. The same will be true for natural numbers. So if I have something like this, a plus 1 equals b plus 1 implies a equals b. This has no truth value, but I somehow want to be able to say that if this thing is true in natural numbers, then I will say that this thing is true. So truth is model dependent. It depends on where you're discussing your axioms and your strings somehow. განმარტებით, by definition, truth will be defined in terms of a model. So in natural numbers, what it means by that 2 plus 3 is 5 is true. I will not discuss this. However, I will say that I will give my strings the meaning 1 and 0, so truth and false, dependent on the model that I'm discussing it. For example, this will have value true in Z, but this will have value false in matrices, for example. But this is just besides the point. So what I want, this is where I'm going to. So in my case, so I constructed my language, I constructed my thing. So my model will be natural numbers. And plus and dot will now, in natural numbers, they will mean addition. So let me give you a definition and you'll see. What is evaluation? Valuation is plugging in constants for variables and constant symbols. So it's a function that for every constant and every variable other than 0 and 1, so 0 and 1 are also constants, right? So I bend 0 and 1 and I look at all variables and all constants and I just plug in numbers. This is my valuation. For example, if I look at this one. If I look at this thing here, so my valuation will plug in some numbers. So for k, it plugs in, let's say 4, then it will be 2 times 4, this would be 8. So it does things like this, you'll see in a moment. And for p and p1, it also plugs in something, right? So it basically for every variable and every constant, you plug in something. That's what valuation is. And now I want to extend it to the whole expression, so to speak. So I plug in for v1 and v1 0, but what about v1 plus v1 0? For 0, I always plug in 0. For 1, I always plug in 1. And for a plus b, this string a plus b, I plug in phi a plus phi b, and a times b, I plug in phi a times phi b. But there's a crucial point here, by the way. This here on the left, this plus, means nothing. This is just a syntactic string, A, the symbol plus B. But on the right side here, this is an addition of natural numbers. So before, if I had A plus B, a string, after I apply phi, I have some natural number plus some other natural number. So what evaluation is doing is looking at the strings and it's plugging in for variables the numbers, specific numbers. So if you plug in different numbers, it will be a different valuation. And also for multiplication, this is just a string on the left side and it's really a multiplication of numbers on the right side. This is what it says here, that there's an overload of notation, that plus and dot here mean the string plus and dot, and here they mean really addition and multiplication. And when I talk about all valuation phi, this means I will range over all past possible values for variables and constant symbols. So now I will say something like this. Maybe should I say it already? Where is it? Yeah. So sometimes I will say for all valuations, that means all possible plugging ins of variables and constants, but I always demand that 0 goes to 0 and 1 goes to 1. But the left side 0 is just a string 0, and right side 0 is a real number 0. Again, the same thing with 1. So when I talk about all valuation, I talk about all the ways I can plug in, as I said, variables and constants. I repeat myself. Now, first, look, the thing here, so in my alphabet, I'm not able to write down 3, right? because I do not have it in my alphabet. However, I'm able to write down 1 plus 1 plus 1, something like this. This is a term, because 1 is a term. 1 plus 1 then with the parentheses is a term. If this is a term, then this is also a term. So this I would call just 3 with a bar on top, meaning that this is just a string. This just represents the string here. By definition, 3 with a bar is just string 1, 1, 1. It's not a number 3. You should think of it in 2 ways. So this is what says n with a bar is just a term, so it's a string, it's an expression of n many ones, right? So this is how, so 0 bar is just 0 and n bar is just this. Because this is the only way I allow this to happen. Because I want, see, if I have, when I defined terms, I said variables are terms, constants are terms, and if I have 2 terms, a plus b with parentheses is a term. But you do not really need this, because otherwise it would be ambiguous. Like if I have something like this, and then I apply valuation to it, and I think of them as real numbers, like 1 plus 1 plus 1. What does it mean? Are you doing this operation first or this operation first? It turns out it doesn't matter, but if you write this here, it's kind of unambiguous what you're doing. But that's besides the point now. This is why I did this in the first place. But now, let's say I have a predicate A. So predicate is something that has a truth value. So let's say A plus B equals C. So this would be a predicate. And let's say I have free variable x in there, and I have a term t. Instead of, I can substitute x with term t. And this is what I will denote by axt. So any predicate I have, something that has truth value, and it has a variable x sitting in there, instead of x, I can write the whole expression in there. So a term, and I will denote this bar x is substituted with t. So it's a predicate obtained by substituting all free occurrences of x in A by t. This is just a notation. So why do I need this? So now I will define what does it mean for a string or a statement. So the statement is just a string which obeys some rules, which I've told you to think of it as having a truth value, to be true. A string A equals B is true if and only if for all valuations phi A equals phi B. Meaning, so I have a, think about it. So I have a statement A equals B. So what does this mean that the string is true? Anything I plug in for A and B, plugging in means you plug in for variables, constant, and then you're extending it this way. Anything I plug in, the equality holds in natural numbers. So I push the definition of truth to natural numbers. Somehow, I hope that we all know what it means that something is true in natural numbers. If you do not know what it means something is true in natural numbers and you're so philosophically inclined, you can look at Tarski definition of truth and stuff. So people do that as well. But okay, A equals B is true as a string if anything I plug in for all valuations, this thing is true in natural numbers. This string is true if A is not true. This string is true if A is true and B is true. A is true or B is true. This is true if not A or B is true. And this string here, I will say, is true if there exists a natural number such that when I plug in that natural number for x in A, the statement is true. So before I was talking about these things as if they were these things. But now I'm making a clear distinction. What is syntax and what is semantics? This is semantics. This is purely syntax. Computers operate on syntax. Our brains think they operate on semantics. So for any x in A is true if for all natural numbers, if I plug in n bar, which is just a string, for x, this predicate becomes true. Okay, So as I said, I'm sourcing my truth from the model, which is natural numbers. And by model, I just mean that I have a valuation, and yeah, I'll already define, so all possible. So the attention is that the first line gives the implicit universal quantity over constant symbols. Right-hand side is formulated in hopefully precise subset of natural language. This is brushing under the rug, meaning what does it mean that something is not true? We're not asking this question. What does it mean that 2 plus 3 is 5? This sentence is true. We're not asking this question if 2 and 3 are natural numbers. But if 2 and 3 are strings, like 1 plus 1 string or whatever, then I know what it means that something is true, because it's true in natural numbers with evaluation. Okay, now I told you I gave each statement a truth value, something is true or not, depending on if it's true in natural numbers or not. And now I have to tell you what are the axioms of natural numbers. So what are things that I take for granted as true? And it's not going to be discussed quite in detail, because there are many other things, but I will give you the gist. So what is the gist? So we'll skim over some things here, because if you go all the way from 0, you'll see in the end. So this is what Russell and Whitehead tried to do, and it doesn't lead to good results. But anyway, so what are some things that I consider to be true? These are the things. First of all, I have to consider things from logic, meaning if I have a Boolean expression, so expression in x1 and xn that has a Boolean value of 0 and 1, if this has value 1 for all valuations of x, I want to consider it as an axiom, meaning, for example, something like this. Let me give you an so excluded middle. Let's take that. So for example, this here, A or not A. I want this as an axiom. So this has nothing to do with natural numbers. This is just a logical axioms. I also take them. So this is always true. No matter the valuation of A I take, it will always come out to be 1. This phi of this thing will always come out to be 1, no matter what valuation I take. So things like, if A implies B and B implies C, then A implies C, and things like this. So there's a couple of them. So I just take all of those tautologies as my axioms. I want those things. And I also want to do something like this. So these are called tautologies, the things that are always true, the ones that I wrote like this. And if you have a tautology and I have some statements, if I plug in my statements in a tautology by substituting, that should be an axiom, meaning that, so if I know this, and now I have two statements, let's say, x equals, for any x for any x and any y, x equals x plus y. This is a statement. And now if I plug in this here, meaning this or not, well, I should write not any x, any y, x equals x plus y, so something like this. This should again be an axiom. Meaning, so I had this thing here, and I plugged in the statements inside here, and then so this should also be an axiom, meaning that x or not x is an axiom, meaning for x I can plug in any statement. So άμα თვის კონკრეტულად tautologiები რაც არის, the things that are tautologies, I can plug in anything in there. So let's just Google this thing and I'll show you what I განახებ. Tautology logics. We want logical tautology. Oh, here it is. So it's things like where is it? So things like this, for example. A or not A. It's something that is always, so things that come from, so if A implies B, if and only if not A implies not A, not B implies not A. So things like A implies B and B implies C, then A implies C. So these logical rules that are always true, but now what I'm saying, for A and B, I can plug in any statement. Any predicate that has truth value can be plugged in for A and B, right? So instead of only having these axioms, I also have, so not only, but having, because, so let me, if I cannot take, I'm building my proof system, right? This cannot be an axiom because what is A and what is not A. So I take this scheme and any predicate I have, if I plug in any predicates here for A's and B's and not A's and stuff like this, they will become an axiom. So I have now infinitely many axioms that are built by this scheme. That's what I'm trying to say. Exactly. So what we're claiming is that we have statements here, so the strings in our language, they can be put in this scheme of my axioms. This is what you're doing every day when you're proving something. When you're proving something, you're using that, okay, if I have statement P1, and it implies statement P2, and P2 implies statement P3, then I conclude that P1 implies P3. You do this, but somehow you do this, but I formalize it now that you're allowed to do this. I gave you some tautologies like this, so these are like rules of logic, but instead of A and B's, you're able now to plug in statements. This is all this thing is saying. These are just tautologies of what? First order logic or whatever. I will show you what else do we want. First, we want tautologies, right? Maybe there's a break already. Yeah, there's a break, so let's take a break and then... Okay, let's continue. So, I mean, we're overcomplicate. Do not overcomplicate this first definition. So, by the way, this, as I said, this phi is not quite the same as this phi, even though this phi in spirit is the same. So what this phi does, this phi plugs in natural numbers for variables and constants, and plus and multiplication for string plus and string multiplication, and it infers the truth value coming from natural numbers. Whereas this phi takes a tautology. So actually we discussed one example, so let's do it one. So if you take three variables, let's say, so if you have, this was the example we discussed here. So this can be x1 implies x2 and x2 implies x3. This thing, I don't know, implies that x1 implies x3. So this is a tautology. Tautology meaning that if you take phi from x1, x2, x3 to 0, 1, so now I think of this phi as plugging in truth values. So maybe instead of 0, 1, I write true and false. So anything I plug in here, so true, true, maybe true, false, then true, false, right? Is that true? Well, this is not, so this cannot happen, but I mean, you get the point, right? So let's plug in, my thing died, so I have to do this. So anything I plug in here, any valuation I plug in, this will be a tautology, this will always be true, right? If this holds, then this will hold. So any variation of plugging in truth and false, this A, x1, x2, x3 will always be true, right? So this is the definition of tautology. Anything I plug in, but this phi now plugs in true and false, it will come out to be true. So this is a definition of tautology. This is what this guy says here. So in A, if I plug in any truth valuation, I will always get true. But what does it mean? Now, I want to be able to use this logical deduction rules and logical axioms in my number theory, so elementary number theory. So I basically, instead of x1s and xn's, I plug in my statements. For example, just give you one more example, and I'll shut up about this. So if your AX is X or not X, which is a tautology, not is written this way in our case, this is always true no matter what X is, 0 or 1, true or false, right? Then I can substitute for X any statement about natural numbers. So any statement about the natural numbers or the opposite of the statement will always also be, this will be my axiom basically. So I take this as an axiom. So my axioms are, I take logical tautologies and I plug in all possible, so I have infinite amount of axioms already. Okay? But this is nothing special. This will work. This is true for any theory you come up with in mathematics. This thinks X or not X if you're not an intuition. Okay, let's forget the intuitionistic logic for a moment, but in most of the times you want those things to be true. Okay, what about derivation rules? So you want the modus ponens as your derivation rule, your proof rule. So if you have A and A implies B, you want B. This is the something but there's some other things. What else do I have? I have change of variables will be my axiom. Meaning that if I have some A prime, which is you can get from A by exchanging all occurrences of variable X by X prime, then the things that they are equivalent should be an axiom. That means if I have some statement that has variable X in it, and I change X for Y, I still get the same statement. So the names of variables do not matter. So if A and A prime are the same other than just the name of the variable, they are equivalent. This is also an axiom. This is nothing special so far. I want to discuss one little diversion, how one would work with such things. I will go here very quickly and then you can go back to slides because this is not very important. I will just show you. So AX is a predicate, meaning it has it's supposed to have truth or false value, and it has free variable X, right? It doesn't have a truth value so it has free variable X. And C, a predicate with no free occurrences of X, and C is a constant symbol. Now let's say I have an axiom like this. For any X, AX implies AC. So think about it, what it's supposed to mean. For any X, if AX holds, think of it this way, then A holds for some C. Right? So, well, not some C, for all C. So, if for any X, AX holds, then AC should hold for some constant, because it holds for any X, if you think about it, what it's supposed to mean. So let's say this is my axiom, and I also have the axioms like this, that not any X, AX is equivalent to there exists X such that not AX. So these are logical axioms. If I have anything or any X, AX, this is equivalent to any X, anything or AX, C, I'll just read it out, C and any X, AX is equivalent for any X, C and AX. So if you think about the strings, what they're supposed to mean in a model, they make complete sense. For example, the first one, right? If it is not true that for any X, AX holds, there exists X such that AX does not hold. So these are the logical axioms we use when we prove stuff. So I want to take them as axioms. I want these strings as my axioms. So now, I want this proof rule also. I want to take this. So if AC implies something, that if there exists, so if there is a constant C such that AC implies C, then there must exist X such that AX implies C. Think about it just for a moment. This also makes complete sense. If AC implies C, there exists X, AX that implies C. And I would just want to show you that from this proof rule, from the proof of AC, you can conclude that if you prove for AC, you can conclude that for any X, AX, and this makes sense. So if you take some general constant C and you prove that AC holds, then you prove that for any X, AX holds because C was taken to be a general C. We do this in mathematics very often, but I will show you just how would computer manipulate strings to do this. What you do is you set B to be not A, then BC implies 0 is equivalent to 0 by definition, basic of logic. BC implies 0 is equivalent to 0 being false. here. BC implies 0 is equivalent to 0 or not BC. This is definition of implies, which is equivalent to AC because AC is just by definition not B. So if you have false or not B, this is just AC. The truth value of AC is same as this is just exercise in logic. And by the proof rule, right, there exists Bx implies 0 is the same as 0 or not there exists Bx, which is by this guy here, the first rule here, it's NEX not Bx, and not Bx is Ax, and NEX AX. So this is just a string of manipulations you can perform to prove that if you have AC, you prove NEX AX just by using this proof rule here. So what I'm claiming is you can do such manipulations. Okay, let's go back to what we were doing here and let's give you more axioms. So all this slide represents here is basically I took logical axioms as my axioms. That is all I did. So things, the rules of logics that are supposed to be applied, also the modus ponens is a rule of logic, I took them in, but now I'm talking about natural numbers, so I have to give axioms of natural numbers as well. The first thing I take as my axioms are what is equality, the axioms of equality. So the first axiom I take is A equals A. Okay, this string is my axiom. The second axiom I take is if A equals B, then B equals A. If A equals B and B equals C, then B equals C. This is, by the way, axioms of equivalence relation, if you remember. So these three things I take. So this defines the axioms of equivalence. And now we go to the most important bit, maybe the Peano axioms, the ones that really define natural numbers. So far, I took logical axioms and I took the axioms of equality. So now, let's look at these three first. I say that A plus 1 equals B plus 1 implies A equals B. For no number, A plus 1 is 0. And if A equals B, A plus 1 equals B plus 1. By the way, you might have seen this written as a successor function. What this basically says is if the successor on A and B are equal, then A and B are equal. 0 has no successor. So there is no A such that successor of which is 0, to be correct. And if two numbers are equal, their successors are also equal. And then this is the very important. Can you read what this says? Vai traçamos. Esse axioma raro. What does this axiom say? A is some predicate, some statement about natural numbers. So what does this axiom say? Let's enlarge it. This is one of these things define natural numbers basically. So everything has a successor, and they also need this axiom here. This is actually many axioms. This is just not one axiom. This is an axiom scheme. But anyways. Egrare. Induction. This is induction basically. So the induction you learn must be taken as an axiom that for any predicate, meaning any statement about natural numbers, if this statement is true for the base case, meaning A0 is the base case, and for any x, AX implies AX plus 1, then AY for any y. So it's basically the scheme of, this axiom is what you use when you use induction proof. Okay. And now I also need operations now, multiplication and addition. So I write A plus 0 equals A is an axiom. A plus B plus 1 is AB plus 1, associativity. A times 0 is 0. A times distributivity, A times B plus 1 is AB plus A. And that's basically it. I mean, I didn't list all the axioms of logic, but somehow it's obvious that the things that are
axioms in logic, I can employ them and use them for my statements, and also the proof rules. This was also illustration of a proof rule coming from logic and how you can manipulate things, but anyways. And these are actually things that define natural numbers. And so now I gave you an alphabet, I gave you the language, I gave you the axioms, and I gave you the proof rules. So we have a proof system. Completely formally written out. I want to be able to, I'm able to talk about natural numbers in strings now. And should I talk about this now? Or should we go on to Gödel? So maybe we'll come back to this. Okay, let's just say this. Now let's say I have a set of some statements about, let's say, natural numbers or about anything. A set S of statements is consistent. So I have a bunch of statements. I will call those statements consistent. This is a very important definition. If no statement of the form A and not A can be derived from S. So I have a set of statements. I have derivation rules. I know what derivation. Well, actually, let's make it simpler. So I have a proof system. So I have axioms. I have a language, blah blah blah, derivations. I know what the proof is, and I will say that this proof system is consistent if I cannot prove A and not A at the same time. So let's say I can prove Goldbach's conjecture, and I can also prove not Goldbach's conjecture. That makes no sense. So I want my systems to be consistent. So this is the definition of consistency. With tedious bookkeeping, one can show that if something is provable, then it is true in every model. And if set S of statements has a model, then it is consistent. Okay, think about it for a moment, and then we'll start with, I will very deeply discuss these topics in a moment now. So, but before we just relax and talk about a brief history. So, I think I talked about this, I don't remember. So there was this guy, David Hilbert, a mathematician in a very prominent mathematician in 20th century, who had this Hilbert's program. So the Hilbert's program was the idea that, okay, let's come up with a proof system, basically something like this. So alphabet, language, axioms, and derivation rules, so the proof rules, so that the whole mathematics will be formalized like this. Right? That was his idea, that every statement in mathematics should be derivable from this set of axioms. So let's come up with this. And they actually started doing this. Oops, what happened? I think I just pressed the finish button. So yeah, they started doing this. And there was this very famous philosopher and mathematician Bertrand Russell, and also a mathematician Whitehead. They started to build mathematics from zero, so completely syntactically, without completely from building the proof system of natural numbers and mathematics in 1910, 1913, and the book is called Principia Mathematica, and this is page 200 from that book, so you can see it's completely in strings and completely, you can see what they were doing. And so what happened is then Goedel came along. He was actually attending seminars somewhere what Hilbert was organizing, and he proved that such thing is not possible. So you cannot come up with a set of axioms that are strong enough to capture natural numbers and also capture everything. We'll see it in a moment what this means. Huh? Gödel So I mean, the idea, we're going to prove Gödel's theorems. That's the whole point. We're going to reduce them to halting problems. But again, the history is that these people, I mean, they realized, they wrote pages and pages of this, and there are some stories that if you would go into office of Whitehead, he had this pages like this plastered all over his walls because he was thinking how to derive things. And once Gödel came along, and they knew that their work was doomed somehow to fail because it would not capture everything, it would not fulfill Hilbert's program. Some people say that Whitehead was never the same, but I cannot attest to that. So, the idea here is that this kind of things maybe have a health hazard. But even though Principia Mathematica mathematically is not, so it was proven by Gödel that you cannot do such thing to derive. So maybe 1 + 1 = 2. Maybe let's just Google this and you can see 1 + 1 = 2. Let's see. I think I had Googled this before maybe. So you can see, oh, it goes to images direct. So it's what is this? So this is the proposition. I don't know what this proposition is. 5443. So it's somewhere on page 300 or something. So this here proves this from this one. It will follow that arithmetical addition has been defined that 1 + 1 is 2. So it took them hundreds of pages to get to this point. So you can imagine they were building this from ground zero. And even though, as I said, mathematically it's not very, after Gödel's theorem, it's not very, I don't know, whatever this is, but I think still Oxford rates Principia Mathematica as one of the most influential books of the century or something. Because okay, so what did we do? We defined what it means to have a proof system, and then we constructed proof system from elementary number theory. We did it a little bit in a hand-waving fashion, but we did it somehow. We have an impression, so we know what the language is, just statements. We know what the alphabet is. We have an idea what the axioms are, like piano axioms and axioms of logic, and so we know everything. So we know the proof rules also. So now we move on to Gödel's incompleteness theorems, and we prove this in this class of theoretical computer science because these things completely hinge on halting problem. The proof we present hinge on halting problem. This is not the way Gödel did it, but since we know about the halting problem, we might as well reap the benefits and understand this theorem because you will probably not see it in any other class, at least the proof of it. So this is one of the most misinterpreted theorems and one of the most philosophically, so this captures the imagination of many people somehow, these theorems, so they dive into philosophy and that we cannot know everything. And so let's discuss them, okay? So first of all, I will say what is an extension. So let's say I have two proof systems. We say that S prime, the proof system S, extends S, basically if it has bigger alphabet, bigger language, more axioms, and more derivation rules. So S is a subset of S prime if S prime has more of everything. So whatever you can prove in S, you can also prove in S prime because it has more axioms and more derivation rules, right? But whatever you can prove in S prime is not necessarily you can prove in S because S has less axioms and less expressive, so to speak. Well, here is the dilemma that I just said. So if S is in S prime, if you can prove something in S, of course you can prove it in S prime, right? Because every axiom, the proof in S is also proof in S prime. Okay. So now let's try to memorize the lingo here. Soundness and correctness. A proof system S is correct or sound if all provable statements are true. What this means that everything I prove in my system is true. If my system is not sound or is not correct, it's kind of useless because that means that I prove things that are not true. What I assume now is that everything I prove is true in my model. That actually brings me back to the... okay, let's continue and I will come back to that in a minute. Okay, what is consistency? A proof system is consistent, which I defined 5 minutes ago, but let's reiterate, is if for no statement W, you can prove W and you can also prove the opposite of W. Right? Then I would say that my theorem, my proof system is consistent. The proof system would be inconsistent if there exists a statement for which you can prove the statement and you can also prove the opposite of the statement. Imagine if you can prove something in natural numbers, let's say Goldbach's conjecture is, you can prove Goldbach's conjecture and you can also prove that Goldbach's conjecture does not hold. I mean, then your proof system, that means that the proof system we constructed would be inconsistent, meaning it proves. Contradiction-ებს ამტკიცე თუ ვერ ამტკიცებ ეგ არის consistent. და sound-ი არის რასაც ამტკიცებ ყველაფერი მოდელში მერე ჭეშმარიტია. Okay? Now completeness. This is very important. A proof system is complete if for every statement you tell me, either I can prove this statement or I can disprove this statement. Okay? Then my proof system would be complete. So any statement I come up with, let's say Goldbach's conjecture again, either I can prove it or I can disprove it. Okay? Then I would say that my proof system is complete. So we have consistent and complete and correct. But now let's look at lemma number 2 and you have to tell me why these things are true. If S is complete, then the language of all provable strings is decidable. Remember what we proved in the previous lecture, well, one before that the language of provable strings were not necessarily decidable. I told you all about the story that if I give you a string, you are, in principle, you can enumerate all possible strings that are provable by just enumerating everything and checking if something is a proof or not. However, if I give you a string, you cannot tell me if it's provable or not. But if, in addition, my proof system is complete, then everything that can be proven is decidable. Meaning, if I give you a string, you can algorithmically tell me if it's provable or not. How? This is okay. This probably is there a proof here? Yeah. Enumerate all proofs, as we said. If proof W appears, accept. If proof of not W appears, reject. So one of them will have to appear because my system is complete. So completeness is the paradise I talked about. If your system is complete, everything is either proven or not proven. Think about it. What was maybe if I get into the head of Hilbert, what was the conception? Okay, what is truth in mathematics? Maybe somebody was thinking this way. What is true? Maybe Euclid was thinking this way. Truth is something I can prove. Now, everything has to be either true or false. Nothing can be ambiguous. So everything should have a proof or disproof somehow. I should be able to prove everything and disprove. This was the idea. Then completeness is something where you can do this. You can either prove something or prove the opposite, disprove it. So everything is like Platonic and everything has this nice idea. That is completeness. And if you have that, you can actually do it algorithmically, basically. So if S is complete, then the language is decidable. So again, just to recall, so let's look at this. Consistent is something that does not prove contradictions. Think of it this way. And complete is something that for everything you know, answer this is provable or the opposite is provable. Now, this is the crucial one. Now let's say S is correct and complete, meaning that for every W you can know whether you prove either W or you disprove W. This is complete. And correct means that everything you prove is true in your model. You want this also. Imagine you prove something and it's not true. Then your system is broken somehow. So let's say your system is correct and complete. Then, instead of provable strings, I'm giving you strings which are true in your model. Remember how we did it? for every string now, for every statement in my language, I gave it was true or not, depending when I plug in natural numbers, if it's true or not. So now I'm telling you that I can also algorithmically decide all the true statements if my system is correct and complete. Now, why is this? Let's pause it again. Exactly. So the answer is correct. You just enumerate all possible again. So since you know that, so as you said, so you look at all the proofs. Either you will, again as in lemma 2, either you will find W or you will find a proof of opposite of W. If you find W, you output true because then S proves W and W is true because of correctness. But if you prove not W, then you know that W is false. Okay. Okay, so let's remember this, that if your proof system is correct and complete, then the true statements are decidable. You can algorithmically tell which statements are true. Okay, so this is again a paradise. That means your computer can tell you things that are true or false. And now we go to lemma number 4, which is Gödel's incompleteness theorem. What Gödel's incompleteness theorem says is if S is any proof system whose language is as expressive as LE, what this means, it is bigger, so our language of our proof system that we derived for natural numbers in the previous slides is contained in my S now. So S is bigger. That means you can write down and talk about natural numbers in your proof system. So it's not a trivial thing. So if your proof system is strong enough to talk about natural numbers, what this means mathematically, that your S contains ZE that we derived in the last slides. So that means S, I wrote this, I don't know why, this can be bigger than sigma E and bigger than LE. So this should be some sigma LAR, so such that sigma contains sigma E, L contains LE. My axioms contain the axioms of natural numbers and maybe more. And my derivation rule all contain derivations of natural numbers and maybe more. But the whole point is, so if I have this system which is strong enough to talk about natural numbers, then if F is sound, then it is incomplete. Let's go back here. What this means that if everything I prove is true, right? The sound, this what sound and correct are the same. So S is sound means that everything I prove is true, which I hope is happening. If I prove false statements, that my math makes no sense. But if F is sound, then it is incomplete. That means there exists a statement such that you can neither prove it nor disprove it. So this is the Gödel's first incompleteness theorem.